Hello students, I'm Rashmi Badwa, Assistant Professor of Science and Institute of Technology and Management, Gurgaon from ETCE department. Student, today's topic is next design of FIR filter by frequency sampling methods and Gibbs phenomena. Basically, in the last video, we discussed about the design of FIR filter using window technique and Kaiser window method, the advantage of Kaiser window method and application as well. We discuss about all these things, and now we'll discuss next topic about another windows, that is Hamming window, Hanning window, and Blackman windows. These are the alternative methods for the window. Mm, Basically, these Hanning window, Hamming window, these are the methods for generation of a FIR filter. And when we talking about Hanning window, the hand function of the length used to perform hand smoothing is named after a person who is from Australia. Han is a window function given for the digital signal processing, and the function can be sampled symmetrically, as where the length of the window is and order of the order can be even or odd. So basically, when we discuss about the difference between Hanning window and Hamming window, so the difference between them is that both windows touching zero at both hand. Basically, the difference is that Hanning window touches zero at both end, removing any discontinuity, but the Hamming window stops just shy of zero, means that the signal will still have a slight discontinuity, means that Hanning, just a difference, see the difference, Hamming and Henning, double N and double M. So or what is the purpose of this windowing function in FFT is that enhance the ability, because it enhances the ability of FFT to extract spectral data from signals, and leakage amount of spectral information from FFT showing up at the wrong frequency. And we discuss about their key points and frequency response in this video. Side by side, the Hamming window is also a, a taper formed by using raised cosine with a non-zero endpoint, optimized to minimize the nearest side lobe. And basically, it is in a function to uh, uh, used for a spectral analysis, because it enables a windowing signal to have the perfect periodic extension implicit in the discrete Fourier transform. When periodic is specified, the function compute a window of length L plus 1 and return with the first L points. See, that's its magnitude within dB. This is the M value is in 16. We discuss about the M and N order of the filter. This is just summarize characteristics of this rectangular window. Main lobe is 4 pi by M. आपको ये छोटी छोटी values learn होनी चाहिए. Handing window 8 pi by M. Hamming window 8 pi by M. Blackman 412 pi by M. Main lobe, side lobe minus 13 dB, minus 20 dB, minus 43 dB, minus 58, and peak is 20 log 10 delta, that is minus 21 dB, minus 44 dB, minus 53 dB, minus 74 dB. As wider transition region is compensated by much lower side lobes and thus less ripples. Filter relies with the rectangular handing window, that is back to our ideal filter. This is the realized with the rectangular window. Basically ये जो सारे functions हैं ये MATLAB पे realize किए गए हैं, तो उनका आप just आप इनके जो ये figures देख रहे हैं, तो आप सिर्फ इन्हें स्क्रीन पे रियलाइज कर सकते हैं कि ये मैटलैब पे इस तरीके से आउटपुट आई है, ये मैटलैब पे इस तरह से आउटपुट आई हुई है. That is realized with the rectangular window, and that is realized with the hanging window with M16. Uh, there are the much less ripples for the hanging window, but the transition width has increased. This is the filter realized with the hanging window. You can see the transition width can be improved by increasing the size of the hanging window to M is equals to 40. Window characteristics is the fundamental trade-off between main lobe width and the side lobe amplitude. As window smoother, peak side lobe decreases, but the main lobe width increases. Need to increase window length to achieve same transition bandwidth. Specification necessary for the window design method is like this is the specification. When we see the response of window design method, you can see on the screen that is omega c cutoff frequency, delta is a maximum pass band ripple, uh, delta omega is a transition bandwidth, and delta omega is the width of the window main lobe. This is the delta transition bandwidth. This is this is delta omega. This is h e j omega. This is h g d omega, and this is the response must not enter shaded region. So this is 4 or 5 properties which we realize on the MATLAB or using the numerical. This is the window design method. This property one is that equal transition bandwidth on both side of the ideal cutoff frequency. This is my graph for the filter. So next property is window design method. The peak approximation error in the sideband delta is equals to that stop band. So next property is distance between the approximation error peaks is approximately equals to the width of main lobe, that is delta omega m. Fourth property is a window design method, that is a delta omega and delta omega m. Width of the main lobe is wider than the transition bandwidth. Next property of 5 is a window design method, that is 1 plus delta 1 minus, and the peak approximation error is determined by the window size shape independent of the filter order. These are just property to see the just difference of their graph or the response, nothing else. इसमें आपको कुछ ज़्यादा नहीं पढ़ना. These are the important points. पास बैंड एंड स्टॉप बैंड रिपल. बेसिकली पास बैंड हमारे पास सिलेबस में भी है, डिजाइन स्पेसिफिकेशन ऑफ अ पास बैंड रिपल एंड अ मिनिमम स्टॉप बैंड एटेन्यूएशन. So pass band and a stop band ripple are often expressed in dB, that a pass band ripple is a 20 log 10 1 plus delta p dB, or a peak to peak pass band ripple is a 20 log 10 1 plus 2 delta p and same dB decibels. Minimum stop band attenuation is minus 20 log 10 delta s dB. For example, delta p is your 6%. So peak to peak pass band ripple, apply that formula 20 log 10 1 plus 2 into 6%. So you can find out the 6 percentage 6 by 100. And when you are having a delta s that is 0.01, put this delta s in the minimum stop band attenuation formula, that is minus 20 log 10 delta s, that is 40 dB. The band edge frequencies omega s and omega p are often called a corner frequency, particularly when associated with specified gain or attenuation. That gain is minus 3 dB. Now summarize or a summary of the window design procedure is the ideal frequency response has a finite impulse response, because we know that the ideal frequency response has a infinite impulse response, or to be implemented in practice it has to be truncated and shifted to the right to make as it causal. Truncation is just a pre-multiplication by a rectangular window, and the filter of the large order has a narrow transition band. However, sharp continuity result in the side lobe interference independent of the filter order and shape is Gibbs phenomena. Basically, there is also a FIR filter design by a Gibbs phenomena. कई बार ये क्वेश्चन पेपर में आ जाता है 4 नंबर में स्टार्टिंग के क्वेश्चंस में व्हाट डू यू मीन बाय गिब्स फिनोमेना. So according to DSP, the Gibbs phenomena is to describe a signal with the discontinuity in the time domain requires infinite frequency content, and it practice it is not possible to sample infinite frequency content. The truncation of the frequency content causes a time domain ringing effect on the signal, which is called a Gibbs phenomena. Basically, this Gibbs phenomena on MATLAB is also available. This Gibbs phenomena is used to convert the sine wave into the square wave by adding the number of harmonics to the sine wave using the Fourier series. And if you have the highest number of harmonics, the output graph shows how gradually the sine converts into the square wave. And when we are talking about the effect of the Gibbs phenomena, then the signal being measured has an important role in determining if the Gibbs effect occurs. And if the signal has no frequency content that is truncated, the Gibbs phenomena does not occur. And for example, applying low pass filter to a single frequency sine wave creating no ringing effect. And when we're talking about the Gibbs phenomena with the Fourier series, then the Gibbs phenomena is an overshoot of Fourier series and other eigen function series occurring at a simple discontinuities, and it can be reduced with the sigma factor. Basically, a Gibbs phenomena is an mathematical phenomena also, in which the Fourier series of a piecewise continuously differentiable periodic functions behave as a jump discontinuity. Window with no abrupt discontinuity can be used to reduce Gibbs oscillations, that is Hamming, Handing, and Blackman. So there are the key properties of the window design methods, that equal transition bandwidth on the both side of the ideal cutoff frequency. This is my transition bandwidth. You can see on this figure. Equal peak approximation error. This is the approximation error peak in the pass band and a stop band. Distance between approximation error peaks is approximately equals to the width of the window main lobe, and the width of the main lobe is wider than the transition band, and peak approximation error is determined by the window shape independent of the filter order, that is N. Now, summary of the window FI filter design procedure. Select a suitable window function, specify an ideal response HD omega, compute the coefficient of the ideal filter HDN, multiply the ideal coefficient by the window function to the given filter to give the filter coefficient, equate the frequency response of the resulting filter and iterate if necessary. And then it means when you are increasing m constraint you have given, you have not been satisfied. Now come to the step by step windowing filter design method, that is and not in your syllabus, so you can skip this, but just you can choose a example for general knowledge, so you can see this slide, otherwise no need of this. Next is a property. The edge band frequency of the ideal response if the midpoint between WS and WP. So how to calculate WS and WP? And that omega C, WC is equals to omega C is equals to omega S plus omega P by 2. Put the value of omega X and omega P and you will get the value of omega C. Then omega HD omega is a 1 or 0 if omega is less than 0.5 pi and omega is in between 0.5 pi and pi, then our ideal low pass filter frequency response. when we are computing the coefficient of the ideal filter coefficient HD are given by the inverse discrete time Fourier transform of HD omega. So HDN is equals to 1 by 2 pi minus infinity to minus pi to pi HD omega E j omega and d omega, that is equals to 1 by 2 pi minus omega c to omega c E j omega and d omega, and you will get the sine function, delay, inverse response to make it constant, and the coefficient of the ideal filters. ये steps हमने ऊपर पढ़े थे. Now compute the coefficient of the ideal filter. For our example, it can be done analytically, but in the journal it will be computed approximately using endpoint IDFT, that is inverse fast Fourier transform. इसकी ज़रूरत नहीं है, इतना complicated हमारे syllabus में नहीं आता है. Now come to the time domain aliasing की भी ज़रूरत नहीं है, आपके syllabus में नहीं है, so आप skip कर सकते हैं इसे. And one more topic is the multi-band design. ये भी आपके syllabus में नहीं है, तो आप skip कर सकते हैं. So after this video, we discuss about the Gibbs phenomena and हैमिंग हैंडिंग विंडोज. आप एक बारी हैमिंग हैंडिंग विंडो का भी थोड़ा सा बुक से जरूर टॉपिक कवर कर लेना. कई बार क्या होता है स्लाइड में वो सारी चीज़ कवर नहीं हो पाती, तो आप एक बार उसके, क्योंकि न्यूमेरिकल पार्ट है, तो आप वो बुक से जरूर एक बार देख लेना. नेक्स्ट वीडियो विल डिस्कस अबाउट अ फ्रीक्वेंसी सैम्पलिंग मेथड. थैंक यू स्टूडेंट, थैंक यू सो मच.